project, you have to cover, we have covered starting from chapter 3 until chapter 7, complete chapter 7. Today, inshallah, we'll cover chapter 7.5, lesson 7.5. You can choose any part of any topic or any topic and make a model for it. Make a project about this one. And the project, we are not going to do a presentation or research. I want something physical, something practical. Like what? In this chapter, you can see, for example, chapter 3.2, we talk about the relation between gas pressure and the volume. And we explained the breathing process using this. So I can make model for breathing process that explains the relation between pressure and the volume as follows, this one. Okay, I have closed it, that's bad. And that's it.
Mr. Can you see the chat?
I will see the chat just 1 minute. And that's the modeling, guys. I'm just recording that because I will upload the video and I will not see it again. So this is modeling for breathing process. Okay, you use a bottle and use balloons and use different things to make model. You can use your own imagination to do it, or you can search the web for something like this. So that's modeling for the relation between the gas pressure and the volume and explaining the breathing process using it. And this is how you can do it, something as a project. Let's explain it. So all of you are not supposed to do the same one. You can choose any different topics. As I told you before, we have covered all these lessons. Choose any part, make search, and find a project about it and do it. Be creative, okay? Anything that you like it. Let me see what is in the chat area. Muhammad Sadiq can't join. Why Muhammad Sadiq can't join? Nobody's here in the lobby.
Mr. He said that he has problems with the internet.
I don't know how to solve it. So I'll give you another example. If you open chapter 3, section 3, for example, let me see what we have here. What's this one? Yeah, this section 3. Here is talking about phase change. You can make a panel, for example, and use models for solid state, liquid state, gaseous state, whatever you want to do, and do it, express the relation between them, and expressing this phase change. You can type this one, for example, type phase change modeling and search the tube. I want something, or phase change projects. This is keywords. You can use it in your search in the web and find a suitable project that you like it, then start to do it. Okay, guys? So and so on. We have covered from chapter 3.1 until 7.5. We'll take it today. Okay, guys? And also we'll take 8. You can wait and do on chapter 8 if you like. But I think that is good for you to start on your project from now. So search the book, surf your book, and find the suitable part that you like it, and then take the name, for example, take this name and type beside it modeling or projects in the YouTube or Google, and find how to do project about it. It's easy, guys. Okay, it's easy. So do this. This is important. You will not have a mark of project unless you do that. It's individually. You cannot do it in the groups. You can do it with your own self.
What is the deadline?
The deadline by the end of the quarter.
When is it?
After 4 weeks or 3 weeks, I'm not sure. Let's make it 3 weeks. Okay? So you will not have your marks unless you do that. You will not have your marks unless you do that. And in one, we have only 12 right here right now in the session. All of those who are not here, please, guys, tell them. I will remind them, and I will upload this video that explains it, and then they can do their project. But give them a hint and tell them that they have to do that. So that was the most important thing today, by the way, to do your project. And let's go to our lesson today. But before we go to our lesson today, I'm going to refresh your mind about the last or the previous lesson. What is rate of chemical reaction? Yes. What is rate?
I just come. What is the project?
Oh, I will upload the video, then you can listen. What is the project? What is rate of, or can you ask one of your friends? Chemical reaction. I want the definition. What is the rate of chemical reaction? What is the rate? I'm supposed to write there. What is the rate of chemical reaction? Not the rate. So start answering this question, guys. What is the rate of chemical reaction? What is the rate of chemical reaction? I want you to answer this question from the previous session, guys. Previous issues. How fast chemical reaction can occur? Bravo, this is good answer. What else? We want more specified answer from the book. You have the definition in the book. How fast? Yes, but there is a definition in the book. The rate at which. It started with the rate at which, because when we talk about describing chemical reaction, but only how fast. The rate at which reactants change into products over time. Bravo, Abdullah Dehlan. Great, 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 great. That's the question, that's the answer I wanted. Another question, what factors, what are factors that affect chemical reaction? What are factors that affect chemical reaction? Yes. Ibrahim Adil said how fast chemical reaction can react and the rate of which reactants can join to. Bravo, Ibrahim Adil, excellent. Surface area, Muaz, yes, we have 5, by the way. We want the 5. Temperature, number 2. And what else? We have 5 factors that affect the rate of chemical reactions. What are those 5 factors that affect rate? Steering, number 3. Surface area, we said surface area before, we still 3. Surface area, temperature, steering, what else? Concentration, excellent. Concentration or the pressure. Factors of the reaction include temperature, surface area, concentration, steering, and catalyst. Bravo, catalyst. So, Abdullah Dehlan, bravo, great answer. So we have the 5 reactions here, the 5 factors. Temperature number 1, surface area number 2, concentration 3, concentration or pressure, steering 4, and the catalyst is number 5. Catalyst, yes, catalyst. Okay, guys, catalyst. Thank you, guys. That was a reminding of the rate of chemical reaction, or how fast the chemical reaction can occur, and the factors that affect that. Today, inshallah, we'll talk about equilibrium. Let's listen to this video about equilibrium. Equilibrium. Let's listen to a video about equilibrium. Okay. We have finished that. Let's do that. That's it.
With a blend of brain nutrients, S26 Pro Kids Gold supports your child's cognitive development.
قهوة ستاربكس هوليداي بلند الجديدة لماكينة نسبريسو الآن في السوبر ماركت والمتاجر الإلكترونية.
In today's video, we're going to look at reversible reactions and see what we mean by the terms equilibrium and the position of equilibrium. Now, most chemical reactions look something like this, with the arrow in the middle pointing to the right to indicate that the reactants can turn into the products. This means that it's a one-way reaction. Once the carbon dioxide is formed, it won't break back down into carbon and oxygen.
So this is one-way reaction. Once carbon dioxide is formed, it can't go back in the opposite direction and form carbon and oxygen. That's, we call it one-way reaction, and we represent it by an arrow that pointing towards the right, as you see here, right here. Let's continue.
In other reactions, though, like this one here, we have a double arrow, which tells us that the reaction is reversible.
So when you have a double arrow, this means this reaction is not one-way reaction. It's a reversible reaction. It goes in either way, toward the products and toward the reactants. So if NH4 ammonium chloride formed ammonia gas and hydrochloric acid, they can react with each other again and form ammonium chloride. So that's possible. That's why we call it a reversible reaction. The reactants turn into products, and the products can react again with each other and form reactants. That's why we call it reversible reaction. It goes in either direction, in both directions. It's not like the previous one. The previous one was only one-way reaction. It's not reversible reaction. So we can divide chemical reactions into 2 types, reversible reactions and non-reversible reactions.
top arrow tells us that ammonium chloride can break down into ammonia and hydrogen chloride, which we call the forward reaction, while the bottom arrow tells us that the ammonia and hydrogen chloride can also combine to reform the ammonium chloride, which we call the backward reaction. So because both of these can happen, we call it a reversible reaction.
So we have forward. Forward means you move from reactants into products, and backward means the products will react with each other and form reactants one more time. That's we call it reversible reaction. That's why we have half arrows, one forward and the other one is backward.
Now, the important thing to understand is that the forward and backward reactions can take place at different rates. At the beginning of the reaction, there'll be loads of ammonium chloride, but no ammonia or hydrogen chloride. So the forward reaction will be really fast, but the backward reaction won't have started yet.
Here he's talking about the beginning of the reaction. You didn't start with products, that's logic. You start only with reactants, which we have here NH4 ammonium chloride. We have loads. All the medium is NH4Cl. There is no ammonia or hydrochloric acid. They are not formed yet. They are products of the initial reactant that we have. So we have loads of ammonium chloride. We have nothing of ammonia and HCl. That's why the forward reaction is fast and there is no backward reaction. That is in the beginning of the reaction. The forward is so fast and the backward, there is nothing in the reactants and the products to react with each other and form the reactant again. So the backward is zero. There is no backward in the beginning of reaction. And the fast is, the forward reaction is so fast. That happens in the beginning of the reaction.
As the reactants turn into products, though, the forward reaction will slow down and the backward reaction.
With time, this one will slow down because you form more of the products and the backward reaction will increase. We have different rates. That's what we are explaining right now. Forward reaction is fast and zero for backward in the beginning. After a while, we have formed enough of the products that they will react with each other and go in the backward direction. So we will increase the rate of backward reaction. That means that the forward will decrease, it will not be fast anymore, and the backward increases gradually. So we have different rates for forward and backward reaction. That's what we are explaining here, guys.
Reaction will speed up. After a while, the rate will even out, and the forward.
After a while, the rate will even out. This means the two rates will be equal. Forward rate will equal to the backward rate. There is reaction in the forward, and there is reaction in the backward. But the amount of molecules that react here equal to the amount of molecules that react in the opposite direction. So if we start, for example, if we start with 10 molecules of ammonium chloride, we will end up into 10 molecules. This is at equilibrium when they even out. Even out means the forward and the backward reaction are equal. This is the meaning of even out. So if we even out forward and backward direction, it means if we start, for example, with 10 molecules of ammonium chloride, we will end up with 10 molecules of ammonia gas and hydrochloric acid and the 10 molecules of so 10, 10, 10. That's what it means. This is for forward reaction. In the same time, in the even out time, we have 10 in this direction and the 10 of ammonia gas and the 10 molecules of ammonium hydrochloric acid will react together and form 10 of ammonium chloride. So the rate of forward reaction equal to the rate of backward reaction. We have reaction happen in both directions. They are not stopping. They are continuous. But they continue with the same rate. We have equal rates. So we started with not equal rates. We started with different rates. In the beginning, the forward was fast and the backward was zero. And with time, we reached to an even out time or even out point. In this point, the forward rate is equal to the backward rate. That we call it equilibrium. And not only equilibrium, we call it dynamic equilibrium because there is reaction happening in both directions, but the reaction to the right equal to the reaction to the left. That's why we call it dynamic equilibrium.
And backward reactions will be going at exactly the same speed.
So same speed for forward and backward. This means we have reached equilibrium.
At this point, the concentrations of the reactants and products won't change anymore.
And now right now, mister, there is reaction here happened to the forward. We take more of ammonium chloride, and there is more formed, the same amount is formed in the backward direction. That's why the concentration of ammonium chloride, or the concentration of the pressure of ammonia gas, or the concentration of hydrochloric acid will be the same, will not change anymore at equilibrium. Because if we started, as I told you, with 10 molecules dissociate from ammonium chloride to form ammonia gas and the hydrochloric acid, and the same times 10. So if we take 10 to the right, another 10 will be formed to the left from the backward direction. And the same applies for ammonia gas and the hydrochloric acid. The concentrations of them are stable or fixed, or will not change anymore after reaching the even out point or the equilibrium point.
So we can say that the reaction is at equilibrium. So to clarify, at equilibrium, both reactions are still happening, but they effectively cancel each other out.
So at equilibrium, both reactions, forward and backward, he means, are happening, still happening. But they cancel out each other because they happen at the same speed, at the same rate.
So there's no overall change in the concentrations of the reactants or products. Of course, in reality, the molecules are still breaking down and reforming, but because they do so at the same rate, there's no overall change in the concentrations. Now, something to point out here is that just because the concentrations of the reactants and products are constant while at equilibrium, does not mean that they're the same as each other. For example, they could be...
Oh, you have to understand this. If we said that the concentration of them are not changing, this means they are not equal. This does not mean they are equal. So this could be concentration of 1, this could be 3, could this be 4. They don't have to be the same concentration, but they have the same concentration for each one of them. They have fixed, are not changed for time. And I will explain this right now. Let's see that.
Lots of ammonium chloride and only a small amount of ammonia and hydrogen chloride.
So at equilibrium, we could have a large amount of ammonium chloride, small amount of ammonia gas and hydrochloric acid, a small amount. So this at equilibrium, for example, we'll take 10 molecules to the right and 10 molecules to the left. We will continue to have the same concentration for ammonium chloride, the same concentration for NH3L, and same concentration for HCl. You see that they don't have the same concentration, but the concentration for each one of them individually will be constant at equilibrium point. So we have a large number for concentration for ammonium chloride, and it will continue the same, or continue fixed, or not change during the equilibrium point. And we have a small amount of ammonia gas, and still a small amount during what? During the equilibrium. So what I mean by equilibrium does not mean they have the same concentration. They have different concentration. Okay, they have a different concentration.
Or there could be lots of ammonia and hydrogen chloride, but only a small amount of ammonium chloride.
Also, the opposite could be happen. So to reach the equilibrium, that does not mean they have the same concentration.
In either case, though, as long as the forward and backward rates are the same, then the reaction would still be at equilibrium. However, what would change when we have these different concentrations is the position of the equilibrium.
So what it changes in the reaction if we have these cases? The first case, to have a lot of ammonium chloride and less amount of ammonia gas and HCl. And here in this case, we have a lot of ammonia gas and HCl and less amount of ammonium chloride. So what it changes in both of them, that's the position of equilibrium. He is going to explain right now the position of equilibrium. In this case, in front of you right now, the position of equilibrium is to the right, is toward the higher concentration. We have equilibrium, the same meaning of equilibrium, the rate of forward equal to the rate of backward reaction, but the position of equilibrium is toward the right, near the higher concentrations. The previous one, where we have a large amount of ammonium chloride, the position of equilibrium will be to the left. Let's see that.
When there are more products, like this, we would say that the equilibrium lies to the right.
So the equilibrium lies to the right when we have more products concentration. When we have more product concentration at equilibrium, we say that the equilibrium lies to the right. When we have more reactants, we say that the equilibrium lies to the left.
But if we had more reactants and fewer products again,
This is the other case. More reactants and fewer products, that then at equilibrium would say that the equilibrium lies to the left, near the reactants.
then we'd say that the equilibrium lies to the left. This position of equilibrium can change depending on the conditions.
Okay, the position of equilibrium to the right or to the left, we can change it according to the conditions of the reaction itself. We can change the position of equilibrium according to what? According to the conditions, temperature, the amount of gases, the concentration of ammonium chloride or concentration of any one of them. We will see all of this. So we can change the position of equilibrium according to the changing the condition of the reaction itself.
For example, adding heat to this reaction encourages the forward.
Adding heat here, adding heat will urge what? Will urge the forward direction. So will affect greatly the forward direction here and will increase the amount of ammonia gas and the hydrochloric acid is produced. So adding other condition, which is heat in this case, it will make the reaction move, instead of lying to the left, it will make it move to the right and lies to the right. This means it will increase the amount of ammonia gas and hydrochloric acid that is produced.
Reaction, meaning we'll have relatively more products as the position of equilibrium moves to the right.
You see what happens?
Forward reaction,
With heat,
meaning we'll have relatively more.
notice what's happening. We started with large of ammonium chloride and we'll end with a small amount with heat. You see what happened?
More products.
That's it. You decrease the amount of ammonium chloride and we change the equilibrium point to the right.
As the position of equilibrium moves to the right.
That's it. It moves to the right with heat.
On the other hand, if we cool the conditions of our reaction,
If we use the opposite, we cool we put it in a cold bathroom, okay? Bath water or bathtub, we put this reaction into a cold environment. What would happen?
it would push the position of equilibrium back to the left. So it
will reverse it. It will move the position of equilibrium far to the left. So it will increase the amount of ammonium chloride, as you will see right now.
More ammonium chloride again.
Again, more ammonium chloride. So we can manipulate the position of reaction according to changing what? The condition. And there is rule for this. It's called Le Chatelet principle. We will see it right now.
Regardless of its position, though, equilibrium can only be reached if the reversible reaction is done in a closed system.
So equilibrium could be reached if this reaction happened in a closed system, whatever the conditions that you're using. So the reaction to reach the equilibrium, it must be happen in the closed system.
Which means some kind of sealed environment from which none of the reactants or products can escape.
So this means closed system means what? None of the reactants or products can escape. This is called a closed system. So you have a closed system, so we can apply the principles of, or the equilibrium point can be reached if the reaction is happening in a closed system. So we can't reach the equilibrium at any position without a closed system, which means none of reactants or products can escape. They will remain in the medium of reaction.
Because if the products kept escaping, it would never reach equilibrium.
Because of the, for example, we form a gas here. The gases leaves the medium of reaction. We can't reach equilibrium. We can't reach equilibrium. We can't increase the rate of backward direction to reach equilibrium. So equilibrium will not be reached in open system. It must be, it will be reached only in a closed system,
The last thing we need to cover is that reversible reactions are always exothermic in one direction and endothermic in the other.
So reversible reaction is exothermic in one direction and endothermic in the other. So we have exothermic, for example, in the forward for exothermic, the backward will be endothermic, and the opposite happen. If the forward is endothermic, the backward will be exothermic.
For example, in this reaction, which shows the thermal decomposition of hydrated copper sulfate to anhydrous copper sulfate and water.
So this reaction, we have hydrated copper sulfate and anhydrous copper sulfate and water. This is a chemical reaction and reversible reaction.
The forward reaction is endothermic.
The forward is endothermic. For sure, the other one will be what? Exothermic. So they must be opposite of each other. If one of them is endothermic, the other one must be exothermic.
And so the backward reaction is exothermic. If you're not familiar with these terms, hydrated just means that water is present, and anhydrous means that there's no water. Now, because the forward reaction is endothermic, it requires heat energy from the surroundings to work. So if we were to heat some hydrated copper sulfate.
So the word endothermic means it needs energy. It needs to be provided with energy for the reaction to happen in the forward direction. So if we heat it up, we'll increase the rate of forward reaction because it needs the heat, the forward reaction.
Which exists as blue crystals, it will drive the reaction to the right, which evaporates off the water and leaves white anhydrous copper sulfate powder. If we then took away the heat and added some water to this powder, though, it would drive the backward reaction. So the equilibrium would shift to the left and reform our blue crystals of copper sulfate. And because this reaction is exothermic, it would re-release all of that energy it had just absorbed in the forward reaction. So to quickly recap everything, reversible reactions are those with a double arrow in the middle, which shows that they can react in both the forward and backward directions, one of which will have to be exothermic and the other endothermic. And if these two rates are the same, then we say that the reaction is at equilibrium, and the concentrations of the reactants and products will remain constant. The position of equilibrium can change, though, and will shift to the left or the right, depending on the conditions. Anyway, that's all for today.
So we have explained what the meaning of equilibrium. In this lesson, in our lesson, we will cover things about equilibrium. Okay. So we will define not only chemical equilibrium, we'll talk about physical equilibrium, and we'll talk about factors that affect equilibrium or conditions that we give a hint about it. We'll talk about it in details, and we'll talk about Le Chatelet principle, which explains how to deal with these factors. So we still have more about this lesson to talk about it. But right now, let me give you just some questions about equilibrium for today's lesson. Let me just give you a small question about it. Just to give you, if you are not familiar with some questions, just repeat it again. That's only a beginning for some few questions that you can think about it. That's the link. For those who joined to us late, I have talked about a project that you have to do it, guys. And I recorded the instruction for this project, and will upload the video today, inshallah. So see the beginning of this video to know what is the project that you are required to do it. You will not have your marks
Mr.
unless you do your project.
Can you send the link of the video to the chat?
Link of the video that we recorded today or the video that we have explained? What video you ask
There
about
a
it?
video on your screen.
Okay, the video here. You talk about this video, huh?
Yes, about the equilibrium.
You're welcome. Oh, don't forget, guys, to see this recorded session to know what are the instructions to do your quiz, to do your projects. It's important, guys. We have only 5. We will have 23 students. We want 23 students to join us. We're supposed to have 22, 23 students. I will take the absence right now. Let me, since Abbas is here.
Yes, Mr.
Okay. عبد المجيد فرهودة. عبد الهادي.
Here.
Okay. عبد الله العبد الباقي.
Yes, Mr.
عبد الله العبد اللطيف.
He wrote in the chat here.
عبد الله عبد اللطيف wrote here. Okay. عبد الله الدحيلان.
Here.
عبد الله المبارك. عبد الله المبارك. Let me stop recording.